Welcome to CX1104 Linear Algebra for Computing. This is chapter 6.3.2. In this subchapter, we are discussing how to use the Gram-Schmidt to perform the QR decomposition. Let's revise the QR first. QR is a technique to decompose a matrix A into the product of two matrices. The first matrix is called Q and the second matrix is called R. The size of the matrix A is m by n. It can be rectangle. The important point to note is the properties of these QR matrices. If A is an m by n, it can have independent columns or it can have dependent column. It doesn't matter which. If A has independent column, then let's discuss what happened or what do we expect R to be. First, A is m by n, R would be a n by n matrix. So R is a square matrix. If A has independent column, R is invertible. If A has dependent column, then R is not invertible. We will show why this is true in the later slides, but now let's continue with what we expect the Q matrix to be. Now, if R is n by n, the number of columns in Q would be n. What about the dimension of, or the length, or the number of elements in Q? It will be m. So Q is a m by n matrix, while R is a n by n matrix to produce A that is m by n. In such a factorization or QR factorization, we call it the economy QR factorization. Later on, we'll show you that we can have a full QR factorization. Let's further discuss the properties of the Q matrix. The most important property is this. QTQ is equals to the identity. So if Q is m by n, QT is n by m. Q is m by n. Therefore, QTQ is n by m, m by n. This is a square matrix. And not only it is a square matrix, it is the identity matrix. So Q has very special columns. The columns of Q are not only orthogonal to each other, that means Qi transpose Qj will be equals to 0 if I is not equals to j. All the columns of Q are orthogonal to each other. What about to itself? Qi transpose Qi, it is equals to 1. This is the property of octonormal columns. So the columns of Q are very special. They are octonormal columns. Now, let's discuss what happens if we have a n by n matrix. That means A is square. Therefore, the Q would be Rn. The number of elements in each Q is Rn. There will be still n of them. Now, QTQ will still be equals to the identity matrix. QQT will be the identity matrix. So we call matrices with such property orthogonal matrix. Now, sometimes students will be confused with the word orthogonal matrix, but an orthogonal matrix is a matrix that have this property, a matrix that is that has octonormal columns and it is square. You may now be wondering, if A is a square matrix but has dependent column, now TQ will still be I, QT will still be I, but this guy here would become singular. So an invertible matrix Q multiplied by a singular matrix will still be singular to produce a singular matrix square. We will show you how to produce a square singular matrix that looks like this. But as a footnote, what you see is that some of the elements here in the diagonal will be 0, corresponding to the columns of A that are dependent. Let's visit the situation when A is tall, M is greater than N. That's the typical problems that we are faced with. QTQ would still be I, which is M by N matrix. But QQT, because for example, you only have a very few numbers of octonormal columns, QQT is not I. QQT, although it's a square matrix, it is not the identity matrix. In this aspect, QQT is a projection matrix. QQT is a projection matrix, and the dimension is a M by M projection matrix. And a projection matrix, as you will remember, allow us to take a vector in Rm, for example y, and we apply QQT in it, we'll get y hat, where y hat is the least squares approximation of y in the column space of A, or I should say in the column space of Q, which is the same. We will discuss what is a least squares approximation later on in chapter 7.1.4, but now just think of it as y hat being the nearest point we can get to y. The nearest point we can get to y in the space of Q, or alternatively in the space of column space of A. The column space of Q is equal to the column space of A. We'll show you. So we must now be wondering how to get Q from A, and it is through one of the methods is through the Gram-Schmidt process. There are alternative methods, but in this course we are only going to study the Gram-Schmidt process, short form as GS. Now, what does the Gram-Schmidt process do? It basically orthogonizes a set of vectors. Imagine that I have given you a matrix called A. We extract the columns out and we call them x1 to xn. And each of these xi is dimension m. So we have a m by n matrix. We call it W here in this notation to simply say that we are now taking a set of vectors. We don't care how is it ordered. And this set of vectors spans a space. So we are using this notation here. The Gram-Schmidt process basically takes this set of vectors and generate another set of vectors, v1 to vn. Each of these v is still the same dimension as the original x. What now happens is that the dot product between vi and vj equals to 0 when I is not equals to 0. So they are orthogonal sets of vectors. And the important thing is that the span of this space, W, is the same as the span of this space in V. That's the cool idea. In the coming slides, we'll show you the Gram-Schmidt process in detail.